Let's look at the left of each matrix model. An alternative approach to account for cases in which mortalities, annual survival, or fecundity are not constant, regardless of the age of the size of individuals, is to use the Leftovich approach that was introduced in the mid-60s by Leftovich. And this approach, rather than being based on age-specific survival and fecundity rate, was based on size or stage-specific survival. Leftovich model can be useful for the following reason. It is often difficult or impossible to age animals and plants accurately. There are a few cases in which we can track them from birth. We can mark them and track year after year. But in a lot of cases, this is not possible. Many organisms exhibit a high plasticity in body size, making size a poor indicator of age. So in theory, by looking at the size of individual, we could estimate the age. And when the individuals are fairly young, this is reasonably reliable. But for adult individuals, when they stop growing, it's really hard to basically determine, unless you track them year after year, what is their age, given the size. And last but not least, we are focused on age, but actually vital rates such as mortality and fecundity in a lot of cases are more related to the size than to the age of the individual, or the development stage, not just the age. So the size is actually more important than just tracking the age. And because looking at the size, we can also account for this remarkable plasticity in body size. So we can have the younger adult, which are large body size, and have a higher fecundity, for instance, and lower mortality than older adult that happen just to be smaller. So we're going to look at this with a classic case. It's a paper by Brault and Coswell on the killer whales. So this really seminal paper, 1993, described the population dynamics of killer whales. There's 4 developmental stages: yearling, juveniles, mature females, and post-reproductive females. Information on demographic parameters is accurately provided in the paper. So fecundity is stage-specific as reported here. This is the average offspring per mother, already accounting for the fact that not all the females reproduce every year, and also for reproductive success. It is also assumed that sex ratio is 1:1, and then there is annual survival from birth to 1 year old, which is equal to 90%, and annual survival in the other age classes is reported here: sigma 1, sigma 2, sigma 3, and sigma 4. And then, in addition to the Leslie matrix, we have a transition probability for stage class I to stage class I plus 1. And we call this here, because we like the letter, tau 1 and 2 and 3. Tau 1 is the probability of going from the first stage to the second stage, so from yearlings to juvenile. Okay, and all individuals that are 1 year old this year, if they survive to the next year, they will be considered juvenile. The probability of a juvenile to transition to the next class and become a mature female in this case is very tiny when you account for the overall population. And tau 3 represent the probability of a mature female to transition in post-reproductive females here. Our assignment here is that to draw the graphs describing the population life cycle, write the equation that describes the dynamics of this population. We will also simulate the population dynamics in the first 20 years, assuming the following initial conditions, and compute the long-term final growth rate of the stable and the stable age distribution of this population. So if you really want to challenge yourself, pause the video and take your time, try to draw that graph and then to write those equations. It would be a super useful exercise. So here I report how the life cycle is represented with this graph here in the paper. And what you can see here, we have this is how it's reported in the paper. We use usually the survival, but these G1, G2, and G3 are the transition probability from the first class to the second class, from early to juvenile, G2 from juvenile to mature, and G3 from mature to post-reproductive females. P1 represents the probability of remaining in the same stage if the individuals survive to the next year. And P2 and P3 and P4, they respectively represent the same probability for the stage 2, 3, and 4. And yearlings are not reproductive, they're just too small. The juveniles are barely reproductive in some cases, and then most of the reproduction occur in the mature females. And the post-reproductive class, of course, it's not contribute directly, as a really important social term, but it's not contribute directly to the productions of offsprings. Okay? To their survival, yes, but not to their production. So in this case, we again indicate with n 1, 2, 3, 4 at the times t plus 1 the number of individuals in stage 1, 2, 3, and 4 respectively. And we have to report here, to write what is the equation that describes the probability of going from 1 to 2 to 3 and to 4. In this specific case, you can see what is only relevant for the stage 4 is the number of individuals that were in the previous stage last year, and that they survived to these years and transition to stage 4. And this also, we want to describe P4, which is the probability of individuals that were alive last year to be alive also this year, and of course to remain in the same post-reproductive stage. So these terms is indicated in this way. It's equal to the number of individuals of stage 3 times t times their survival at the stage, which is sigma 3 times the probability of transition from stage 3 to stage 4, from mature female into post-reproductive females. And then we can describe the P4 transition terms, which is simply the number of individuals that were already in this class the past year times t, and they survive to these years, so sigma 4. Okay, we can easily do the same in the other one. So we get the number of individuals that are in stage 3 times t plus 1 is equal to the number of individuals that times t the previous years were in stage t times their survival, sigma 2, times the probability of growing from stage 2 juveniles into reproductive females. And then here, look at these terms. We have individuals that the previous years at times t were already in stage 3. Their survival is equal to sigma 3, but the probability, we have to account now for the probability that they're not transitioning from stage 3 to the post-reproductive stage 4. And because we indicated with tau 3, this transition probability, this is actually equal to 1 minus tau 3. And then we can do the same for the stage 2, the juveniles. And then we got to write the renewal equation for the first class. We only have 2 reproductive stages, barely the second stage of juveniles, and certainly the mature female. We account for sex ratio, the per capita fecundity, and then their survival of the offspring to 1 year of age. So, like we did before, we can write this equation in a compact format by using matrices. So we have 4 stages. So we have a 4x4 square matrix in which we have, again, these are the elements to represent the reproductive success of the individuals in the population, and they account for per capita fecundity, sex ratio, and sigma 0. And then we have the elements of the sub-diagonal, the G1, G2, and G3, which are similar to those that we have seen for the Leslie models. And last but not least, we have the P2, P3, P4, which are on the main diagonal. And these are the individuals that were already in this class. So class 2 last year, and then they survived and remain in this class this year. And P3, those that were in the stage 3 last year, and they survived and remain in this class this year. So these are given by sigma 2, 1 minus 2, 2, and sigma 3 times 1 minus tau 3. And we can substitute the value, and we have derived the matrix that represents the transition matrix that represent the dynamics of this population. We can again run all the simulation. We're going to do that together. It's going to be interesting. And as we did before, we can plot the number of individuals in each stages as a function of time and the overall number of individuals, total number of individuals, which is the sum over all the stages of the number of individuals at times t. And we see that there is a fluctuation again in the first few years of the simulation, but then the population starts to grow smoothly in a geometric way. So we expect that if we plot it in a semi-logarithmic scale, this is going to be represented by a straight line. And this is indeed the case. That's great. We can put also the fraction of individual. This is the population size structures in each of the stages. And we see that after the first wild fluctuations, the population eventually level off. And it's going to take a lot of time. It doesn't even reach the stable stage distributions in 50 years because it's a slowly growing population. And we can also plot the finite growth rate year after year. And we see that at the beginning, the population decreases a little bit, given the initial condition, the arbitrary initial condition that we gave. So the finite growth rate was indeed slightly smaller than 1. And then it exceeded 1, it picked off, and then eventually is leveling down to just a little bit more than 2% per year. So a very slowly growing population. There are general properties that are characteristic of Leftovich, and as a matter of fact, as we just saw of the Leslie model that we described here. In the long run, that's mathematically will be for time that goes to infinite. So if we let the transit go away and wait long enough, we can say that the total number of individuals in the population eventually increases in a geometric way with the finite growth rate lambda. So the limit of t that goes to infinite of n total time t plus 1 divided by the total number of individuals time t is equal to lambda. And then the population in each size class or age class goes according to the same Malthusian law. And so we can see here that the number of individuals in each age class grows with the finite growth rate lambda as well. But the proportion of the individuals in each age or size class eventually become constant. So the limit of t that goes to infinite of n of x times t plus 1 divided the total number of individuals times t is equal to pi of x. And you can see here, and I want to stress, there is no any longer the time suffered. So this is just a function of h. Okay. And we're going to take a little break.